Okay, let me then start. So I've got a whole bunch of questions from people here. So let me try and zoom through those, no pun intended, try and zoom through those questions there. So one quite simple question someone asked is, if the rank of a set X is alpha, why is the rank of singleton X alpha plus 1, or indeed successor of X equal to alpha plus 1 here? Recall that S of X is just X union singleton X here. So what is the rank of X? It's the least alpha such that X is a subset of V alpha. And because V alpha plus 1 is the power set of V alpha, this is also the same as the least alpha such that X is a member of V alpha plus 1. So either of these is a good description of it, but this one here is the official definition here at the top. So if the rank of X is alpha, right, because X is a subset of V alpha, right, so the singleton X is a subset of V alpha plus 1, right, because V alpha plus 1 is the power set of V alpha. And here's a subset of V alpha. So here's a subset of V alpha. So X is a member here of V alpha plus 1. So this singleton X is a subset of V alpha plus 1. So the rank of singleton X is less than or equal to alpha plus 1. Okay, so that's one part of the equality here. And you don't now just say it's contradiction to say that it's less than. If the rank of the singleton X was less than alpha plus 1, then we would have that the singleton X here, which after all is a subset of V of the rank of singleton X, here. If this then is less than alpha plus 1, right, then this rank is some Tor, right? Well, it's less than, so this is going to be a subset of V alpha. Because then the rank of singleton X is less than or equal to alpha. So this is a subset of this. But then I'd have X as a member of V alpha, which contradicts. That alpha plus 1 is the least where X is a member of V alpha. So this doesn't occur. So we have it's both less than or equals and greater than or equals. And the rank of the successor of X, which you can see is X union singleton X, that's again alpha plus 1 for similar reasons. right, which I won't go through here. So someone has just asked, okay, for those who've just joined, all I've done is look at why, if the rank of X is alpha, why the rank of singleton X is alpha plus 1. So somebody's just asked, if I've got a function from X to Y, and both the rank of X and the rank of Y equals alpha, then they ask, what is the rank of F? And well, it can depend upon whether X and Y both have rank, a limit ordinal or a successor. So there are two cases. If alpha is a limit, then here, so again, example, think of alpha as being omega. Right? What is F? Set of ordered pairs, right? If F of U equals V, I've got this, officially this ordered pair is in F. And U is in X and V is in Y, because it's a function from X to Y. Then as alpha is a limit, right here, rank of U and rank of V, these are less than alpha, because the rank of X and Y is alpha here. And then if you look at what the rank of the ordered pair UV is, this is also less than alpha. Again, think of this as perhaps being omega and these as being finite. Then the rank of this would be finite. It's the maximum of the ranks of U and the rank of V plus 2. So that is saying then that F is hence, F is also going to be a subset of V alpha. So this implies the rank of F. Again, is going to be alpha. On the other hand, if alpha is a successor, then the answer is slightly different. Right? If alpha is beta plus 1, then, okay, there's going to be a member of X, there's going to be some U in X whose rank is beta. U in X here. With a rank of U equals beta. Okay, because X is a subset of V alpha, nothing smaller. So there's an element of X whose rank is beta. So in that case, this UV here, this is going to have rank in the analysis above. This is going to have rank 2 more than beta, right? Sorry, my pen is running out here. It's beta plus 2. So in fact, once you then carry all that reasoning out, what you've got is f is a subset of v beta plus 2. Here. So the rank of f then is going to be alpha plus 1. Right, so it's something larger than the limit case here. So yes, it's slightly confusing. You have different answers depending on whether alpha is a successor or is a limit. You should check this. I think I have this right down here. Okay, check this. Just going to go and get, just going to get another pen. Okay, just a moment. Checking something. Somebody sent through a question. Yes, so what have I got? The rank of uv here is beta plus 2, so f here should be a subset of v beta plus 3. So this should make the rank of f be alpha plus 2, which is beta plus 3. Okay, I think this is the answer here. Okay. Let's look at some of my, let's see what are some of the other requests here. Okay, so that was exercise 6.1. This top part here is exercise 6.1, number 1, which someone asked about here. Let's go back to 2.9 and 2.10. These were kind of slightly silly exercise here. Size 2.9. It's a function from omega to omega. And it's given by h of k is k minus 10 if k is bigger than 100. And otherwise, h of k is supposed to be h of k plus 1 if k is less than or equal to 100. So you're being asked in the exercise to give a definition to make it look more like a standard recursion, perhaps a definition by cases or something. I mean, see, here the problem is that h of k is being defined not in terms of perhaps previous values, h of l's for smaller l's, but it's actually being defined in terms of h of k plus 1. So this doesn't look like an ordinary recursion. And in fact, you might wonder whether it's a decent definition at all, right? Here. But actually, so then the exercise is give a definition of h, and it says if possible, using a standard recursion, using a format of a standard recursion. So this could be a recursion by cases, right? So actually, well, that's perfectly good here. So whatever h is going to be, it's going to have to be like this, right? So the solution here would be, we'll have h of k is just k minus 10. K is bigger than 100, right? But actually, if you actually play around with this, right, what you can, all that can happen here is that h of k is, this is just constantly 91, right? K is less than or equal to 100. Okay, so, I mean, I'll save time by just not saying why this is, but I mean, if you actually look and plug in these values here, you see that these things here will work. And in fact, if you play around with this 91 here, you'll see actually this is what it has to be, right? For k's that are less than or equal to 100. Right? Because after all, if k equals 100, h of 100 here is supposed to be, well, h of, and well, what is h of 101, right? Well, it's 91. So h of 100 has to be h of 91. But then if you carry on with this reasoning, right, you can then look at what h of 99 is, right? And you see this also has to be 91. And the same for 98. But now this here is in a standard recursion by cases, right? We define what h of k is for k's up to 100, and we've got a perfectly good definition of what h of k's are for k bigger than 100. So this is a standard recursion by cases. Down here. So I think this is all you would have to do in this case. to 10, find infinitely many functions h from omega to omega satisfying h of k is h of k plus 1. And then part 2 is find the unique function from omega to omega satisfying h of 0 is 2, and then h of k is h of k plus 1 times h of k plus 1 plus 1 if k is bigger than 2, if k is bigger than 0. So again, this is something where we define a starting value, but h of k apparently looks like it's defined in terms of h of k plus 1, right? Not of a previous value here. But actually what you've got, you only have to find infinitely many functions. So actually any constant function here would do, right, for this top one here. So it's kind of a trivial or a trick question. Right? Yeah. So pick any constant function here. And actually here, there's only one solution. This is the function where it's value 2 at 0, and it's got value 0 everywhere else. And again, the point is, right, why does it have to be 0, right? Right? If h of 0 is 2, this is supposed to be, sorry, this is supposed to be h of, so what would h of 1 be, right? Here, it has to be h of 2 times h of 2 plus 1. So it's going to be bigger than, if h of 1 is bigger than 0, h of 1 is going to be bigger than h of 2, right? Because it's h of 2 times h of 2 plus 1, right? So if h of 1 were bigger than 0, then h of 1 is bigger than h of 2. And then similarly, if h of 2 is bigger than 0, right, which it would have to be if h of 1 is bigger than 0, we then have h of 2 is actually bigger than h of 3. So we would continue in this reasoning like this. And what we would have is an infinite descending chain of natural numbers, right? Like this, h of 2 bigger than h of 3, bigger than h of 4, bigger than h of 5, which is impossible. Infinite descending chain of naturals. Which is impossible. So this can't happen. So h of 1 is 0. But then the same reasoning says the same thing about h of 2 and h of 3. So this is the only possible function that's here. Okay, so let's do some exam questions. Let's look at this is an exam question from 2019, question 4, B and C. Let me see if I can. Okay. So 4B and C here. Well, let's just look and see what 4A says. So here it was asking you to just give a definition of what a countably infinite set is. And then to give the proof that the union of a countable sequence of countably infinite sets is countably infinite. Okay, so this would be standard book work. So we use this in part 2, part B. So what we have here in part B, it's like looking very, is we've got sets of reals, A1 and A2, and they're of cardinality Aleph 0 and Aleph 1. Right? So countable, and that are the first uncountable cardinal. Then P1 is going to be a set of polynomials. And this is what a polynomial looks like. And if it's got degree n, some finite n here, and the coefficients are all coming from A1. So the polynomials in P1 all have coefficients from A1, this countable set. And P2 is defined similarly, but the coefficients all come from this set A2, which has got size Aleph 1. And you're being asked to say, what is the cardinality of these sets of polynomials, P1 and P2? Okay, so what are we saying? What are we going to say here for this? So we have here, we have A1, which has got cardinality Aleph 0, and we have A2, which has got cardinality Aleph 1. And Pi is going to be the set of these polynomials. So plus A0 here, where each of the AIs come from, sorry, let's call them AJs. These are in PI for n greater than or equal to j, greater than or equal to 0. Here. And for any n in omega. So the polynomials are not a fixed degree, right? So for any n, there's going to be a polynomial in here of degree n. So when we look at P1 here, typical entry into P1 is a polynomial, but really all that the polynomial depends on is this sequence here. So each sequence here corresponds to such a polynomial and vice versa. So the number of polynomials is really just the number of finite tuples from the coefficient set. As there is a bijection, well, the one illustrated, we're going to have that the cardinality of P1 is going to be the cardinality of the collection of these tuples. Right? So this is the cardinality of the collection for all n's in omega, of the collection of functions from n into A1. Right, we vary n because we're not talking about fixed degrees here. And this is the collection of all functions from n into A1, right? I can think of that also as being here A1 to the n. Actually, this is probably a better way to put it. Yeah. So this is the Cartesian product of A1 with itself n times. That's what this is here. But okay, what we have is that the cardinality of this here into A1 here this is, each of these has got cardinality Aleph 0. Okay? So this is just Aleph 0 times Aleph 0 n times, which is just Aleph 0. So we can conclude then that actually this is just countable. Okay, that's the first part. But once you've thought that bit out, then this is really just this reprise where we just take A2 to be another different set of size Aleph 1. Right? Here. All I'd be getting down here is A2, and here I've got Aleph 1 times itself n times. So I suppose I am quite finished here. Here I've just said what the size of this one is here. Is a union of countably many sets. Each of cardinality Aleph 0. So it's a countable union of countable sets. So by part 1, if you like, P1 will have cardinality Aleph 0. for P2, we can repeat the above, but now A2 has cardinality Aleph1. And so now this Cartesian product here, n times of the A2 sets here, this is going to have cardinality Aleph1 times Aleph1. And again, by repeated Hessenberg, this has got size Aleph1. So then I've got that P2 is going to have size Aleph1 because it's the union of countably many sets, each of which of cardinality Aleph1. Is now a union of countably many sets of now of cardinality Aleph1 here. Okay. So one question is, have I made any assumption to equate the cardinalities of P1 and this union? Are there not functions from n into a that are not polynomials? I mean, the thing I'm trying to interpret this a bit. I mean, I think the way to think of what P1 is, of course, it's the collection of these polynomials, but anything in P1, right, is determined by the sequence of coefficients. So there are as many things in P1 as there are finite tuples from A1, right, which is what I've written here. But actually, I mean, a finite tuple from A1 is, again, it's just something in this Cartesian product of A1 with itself n times. So I just calculate the size of this here. And this is what it gives me down here. I mean, strictly speaking, the wording of the question was, are there not functions from n into a that are not polynomials? Well, yes, right? But we are recognizing the fact that every polynomial corresponds from a function, right, from some natural number into A1. And it's this sequence here. I think of this sequence here, of course, as being a member of this Cartesian product. So these things are of the same size. So what I'm also using here is the fact that the union of accountably many sets of cardinality Aleph1 is Aleph 1. Here. So I'm appealing to that fact here at this point. Part C of the question that was also asked about. So this also asked about if now I take 8, 3 as the set of irrationals. So I look at R and I take away the rationals. So this is the set of irrationals. P3 is now the set of polynomials with irrational coefficients. So from A3, then give a calculation for the cardinality of P3. Is this the same as your answer for P2? Okay, discuss, which is just a shorthand for saying, say something about it. Right? Okay, the point here is that so now the size of A3 is the size of the collection of reals minus the countable set of rationals. This is an uncountable set. If I subtract a countable set from an uncountable set, I still have an uncountable set. So these cardinalities are the same. And that's cardinality is 2 to the Aleph 0. Right? Here. So now, so this is the discussion. If CH holds, then 2 to the Aleph 0 is Aleph 1. So the answer then is yes, it would be the same as the cardinality of P2. So in this case, they're the same. But otherwise, if not CH, then what is the size of P3, right? So it's the cardinality of countably many sets, each of size 2 to the Aleph 0. And each of these sets is of cardinality 2 to the Aleph 0. So I've got Aleph 0 many sets times 2 to the Aleph 0 here. Countably many sets, size 2 to the Aleph 0. This is the bigger of the two, so it's this. So cardinality P3 is 2 to the Aleph 0, and that is, well, whatever it is, right? Which we don't know. Okay, so that's that question there. Yes, I mean, I suppose going back here, what I've written in words here, I could have written better as saying, well, the cardinality of P2, i.e., is there are countably many sets here, times each of which has got cardinality Aleph1. And again, larger of the two is Aleph1. This is Aleph1 here. So that would be a better way of putting that there. Okay, I'm aware I haven't got through all of the questions that I've been sent. We'll do hopefully the rest of those, or if you send me any more this afternoon. So I'll say goodbye for now, unless you want to put any questions through to me.